Hello, everyone at home. Welcome back to another Wednesday evening from Cambridge University Astronomy. It's a very rainy day here in Cambridge, so we don't have any stargazing afterwards. Luckily, we're going to make up for it with an excellent talk from our headline speaker, who is Måns Holmberg, who is a PhD student here at the Institute of Astronomy in Cambridge, who works on the atmospheres of exoplanets. So Måns, if you just want to share your slides. I will say some of you have found the YouTube chat box already, which is down there in the corner. Any questions for our speaker, please just pop them in the chat. I'll make sure Måns gets them at the end. So yeah, with that, over to you.
Thank you, Matt. Yes, so my name is Måns Holmberg. I am working on detecting atmospheres of exoplanets. So that's what I do for my PhD research, and I thought I would share some of it with you today. So in the beginning, there were 8 known planets, or rather in the beginning, there was no known planets except our own. But as we looked up in the sky, we found 8 of them in our own solar system. And that was our only data point for quite a while. Then recently, a few decades ago now, we started finding more exoplanets. So just to get a sense for how far away these exoplanets are orbiting other stars, let's have a look at the nearest star to our solar system. So it's called Proxima Centauri, and the distance to Proxima Centauri is around 4 light years. That is a very long distance away. So if we compare that to the planets, so say Earth, if we call the distance from the sun to the Earth 1 unit or 1 astronomical unit, then the distance to Proxima Centauri would almost be 1 million of those units. So it's fairly far away. Then how could we even dream of detecting a planet orbiting a star that is that far away? Well, we can do that. And yeah, so how do we do this? One way is to use the so-called radio velocity method. So we have a star and a planet, and it's not the case that the planet orbits the star where the star is fixed, but actually they sort of orbit each other. So the star is sort of the planet is pulling on the star ever so slightly, making the star wobble back and forth when the planet goes around its orbit. And we can detect this shift by looking at the radio velocity of the star. So if you have heard of the Doppler shift, you know, when an ambulance is going by, changing the pitch of the sound, the same happens with light. So we can look at the light shift being back and forth ever so slightly. And we use what's called spectral lines, so features in a spectrum to look at this. I'll explain that more in a moment. And we can do this. So in 95, Mayer and Queloz, who now has the Nobel Prize, 2019, discovered a very large planet with an orbit of 4 days around a sun-like star. And what is remarkable about this discovery, not just that it was the first discovery of an exoplanet around a sun-like star, is that it was an exoplanet that we did not expect. We do not have a Jupiter-sized object in our solar system with a period of only, so the period is how long it takes to go around its host star, of 4 days. Like for the Earth, it takes a whole year. So for this planet, which is big as Jupiter, to zoom around its star with this great velocity was a surprise. Another method is the so-called transit method. So let's say we stare at a star. And if we are lucky, the planet will pass in front of its host star, dimming some of its light. And when it's blocking some of that light, as you can see in this animation here, right now it's on its way to the backside. So when it's dimming some of that light, we can measure that dip in brightness. And we can do this with either space-based telescopes or ground-based telescopes. And for a big planet like the one I just talked about, the dip in brightness is about 1%. For smaller planets, it's much less. Nevertheless, we can do these observations. So on the right, you see some real data. You see it's a bit more noisy than like this nice curve over here, but we can do this. Another thing to note is that if the planet is very close to its host star, as the one I just talked about, then it's getting a lot of radiation, a lot of light from the host star, making the day side of the planet very warm. It can reach many thousands, so maybe 2,000–3,000 Kelvin in extreme cases. So getting close to stellar temperatures. And when the day side is that hot, it glows. And this glow we can also detect, which I'll come to later. So just to reiterate, planets themselves, they don't shine that much. They do give off some light. They do give off this thermal radiation when they are very hot. But compared to the host star, they are very bright, very dim, sorry. So if you look in the visible, sorry for the technical plot, but if you look in the visible light over here, then these are the solar system planets. If you compare this to a star, you can see that this is a difference of many orders of magnitude. So it's very, very difficult. It can be a contrast of a million or a billion even. If you look in the infrared, so thermal radiation, if you know of a thermal camera where you can see thermal radiation, you can detect the temperature of an object. So if you go to that wavelength, then the contrast is higher for some objects, especially for these hot objects. I'll come back to this in a moment. But maybe the more direct way, and what we wish, is to directly take an image of a planet. Although this is very hard for the first point that I brought up. Stars are very, very far away. So if we want to look at planets directly, orbiting stars, then we have to have very high resolution telescopes. And this is possible. So on the right, you see a picture of the 4 very large telescopes. Yeah, astronomers are very good at naming telescopes. The next telescope after this is going to be extremely large telescope. Yeah, never mind. So we can do this direct imaging of exoplanets. What we do is we have to block out this central light from the star, and what is left is the light from planets orbiting around. And on the left, you can see this. Here you have 4 confirmed planets orbiting a star. So, going to today, we know of roughly 5,000 exoplanets. This is a big contrast to the 8 we knew in our solar system before we knew any exoplanets outside. So, what I want you to take away from this plot is that planets are diverse. So, if you look at this figure on the left, you have the orbital period on the x-axis and the radius on the y-axis. And you can see that planets fill this graph, and there seems to be any kind of planets. We have rocky planets. The 4 rocky planets we have in the solar system is Mercury, Venus, Earth, and Mars. Then we also have lava worlds. So they are also rocky planets, but they're molten. They're very close to their host stars. And you can see the orbit is very small because they are very close to their host stars, orbiting around, getting a lot of light. Then we can also go further out. We have colder planets and bigger planets. So this would be Jupiter-size planets, Neptune as well. And then on the top here, we have this category that I mentioned first. This new category of planet, which we could never have dreamt of to begin with, and it's called hot Jupiters. This was a surprise, and I'm sure we will find more surprises in the future. now that we know of this many exoplanets, one very interesting fact is that we can say with certainty, with statistical certainty, that on average, there is at least one planet per star, maybe more. And that is very exciting because we have only found 5,000 so far. There's a lot more to discover in our own galaxy. So yeah, the frontier is, yeah, we are at the frontier at the moment. One other thing I want you to know is that planet sizes come in two general shapes. So we have rocky planets, which we have found to be very common. But if you look at this peak here, so on the x-axis is planet size, we seem to have two peaks. So this is the probability of finding a planet of this size. We seem to have two peaks, one at rocky planets, and one at 2.5 size the size of Earth in radii. And the interesting thing is that we don't have any of these planets in the solar system. We don't know what they are, which is very intriguing. So are they super Earths or are they mini-Neptunes? We don't know because we don't have them in our solar system. We can only model them and trying to find out what they are. But we can break this degeneracy by looking at their atmospheres, trying to find out their compositions and trying to find out more about their formation history. So a super Earth could, example, could have a small core with high density iron, for example, like some of our core is on Earth, with a large hydrogen inflated atmosphere. Or we can have a mini-Neptune type situation where the core is instead bigger but lighter, so made of, for example, ices and water, where the atmosphere itself is thin with the little hydrogen. So studying atmospheres can teach us about the diverse landscape of exoplanets. But how do we do this? How do we study the atmospheres of exoplanets? Well, as I mentioned before, we use spectral lines. Spectral lines are essential. They are the chemical footprints that we use to categorize what atoms and molecules exist in the universe. That is one of our best tools that we have. So we have our molecules that we can study in the laboratories here on Earth. We can find out what spectral lines they have. So each type of atom and molecule have a distinct set of lines. And we can compare that to what we find elsewhere in the universe. Because we can't go to these exoplanets because they're so far away. The closest star is 4 light years away. That would take very, very long, especially with current technology. So we rely on comparing the spectra. So if we take light from an object, say an exoplanet, we split it up in a rainbow using a prism, for example. And then we can see these spectral lines and compare to what we know. So what we can do, I talked about these transiting planets before, that you have a exoplanet transiting in front of its host star, and then some of the light from the host star will pass through the atmosphere. When that happens, we can point a telescope, for example, the Hubble Space Telescope, that is currently in space and doing these types of observations. We can point that telescope or other telescopes to this event when the planet is transiting, detect the light from the atmosphere, and we can say something about the atmosphere, the composition, temperature structure, and so forth. So here is a fun demonstration of Earth. So this is a picture of Earth in the infrared. This white blob is the moon. Ignore the moon. So this is just an infrared picture of Earth, nothing special. If we go slightly more in the infrared, there is a band which absorbs a lot of O3, which is ozone. And the Earth become more opaque, or the atmosphere become more opaque. So you can see the difference. I will do that again. The radius of the Earth appeared to change. It appeared bigger in this other wavelength band. This is what we do, but for exoplanets. So transmission spectroscopy is what this is called. We have a star shining light through an exoplanet's atmosphere. It interacts with the molecules in the atmosphere. It will imprint some of these spectral lines in the spectrum that we then observe on Earth, split the light up, using a spectrograph is what it's called, but you can think of it as just a prism. Some of the light is scattered away, and we can tell something from that as well. And when we do this, we get a spectrum that looks something like this. You might not think that this is very spectacular, but think of everything that I've just said. These exoplanets, they are very, very dim compared to their host stars. It's sort of like trying to observe the chemical composition of a fly flying near a streetlight, which is a few kilometers away. That is going to be difficult. And that is what we're doing. Except this is a planet. So these data points here show a sort of bump here around 1.4 micron. This bump corresponds to the spectral features of water. This is a detection. This is the first detection, now back in 2014, of water on an exoplanet. So this is big news. Today, we have come further, but this is a great milestone in our endeavor to discover exoplanets. So one other thing we can do, instead of doing this transmission spectroscopy, where the planet had to be in front of its host star, we can look at the thermal emission. So if you have a lot of light from the star heating up the day side of the planet, the day side gets warmer and it radiates in the infrared. So if you take an infrared camera pointed to a dog, it will look something like this. You see that heat is escaping from eyes and mouth. It will look basically the same for a human as well. You can do the same for a planet or any other object. So this is Jupiter. On the right-hand side, there is visible light, and on the left, you have infrared. You can see it. Jupiter is glowing from the heat. But Jupiter is quite far away, so it's not glowing that much. But looking at the emission, so the thermal emission, the radiation from hotter objects, we get more signal, and we can actually do this. So the difference in geometry is that instead of observing the star when it is in front of its host star, we measure it when it's on the backside. One way of doing this is to take a picture when the, so it's shown here on the left side. You have the star, you have the planet going back. You take a spectrum, then you wait until the planet is fully behind the star. So then there's only the stellar light. Take two spectra, subtract the two. What is left should be a planet spectrum only, with the stellar light subtracted. It's going to be fairly dim, but we can detect it. So again, sorry for this technical plot, but on the right here, you see such a spectrum taken also with the Hubble Space Telescope of a very hot Jupiter. It's called WASP-33b. And when we're naming planets, we call them B because A would be the star itself. And what is interesting when we look at this, basically the temperature of the planet, is that we can learn something about the temperature structure of the planet. We can say how hot it is, and we can also even say how hot it is at different depths in the atmosphere. And that is crucial because that will teach us about what kind of chemistries can be happening in these atmosphere. And together with the spectral lines, this gives us a lot of information. So here is an observation of WASP 43b. So this was observed when the planet was going around its host star. So we took infrared spectra throughout the whole orbit, measured the temperature at every point of the orbit, and then we got a temperature profile. So basically the temperature at each point in its orbit. And we even could say what temperature at different pressures, so different altitudes in the atmospheres. So this is current research. This is where we are at. We are learning a lot at the moment. The future is bright. One thing that can destroy or make our observations tricky is clouds. We don't like clouds here on Earth because then we can't see the stars. But exoplanets have another problem. If there's clouds in those atmospheres, we can't see their atmospheres, basically. So we can't infer the chemistries, we can't really see anything. So clouds block the view of the atmosphere, basically. And, well, this is again a technical plot, but what I want you to see is compare to, oh, this was a bit further back. Okay, never mind. Look at the black points here. It's very flat. It's just like a flat line. There is no real structure here. There's small variation, but the error bars are as small as the variation. So we are seeing nothing really. And that's because this exoplanet is cloudy. This was actually, I think it was 15 transits. So we observed this planet 15 times. So when the planet went in front of its host star, waited, observed again, waited, observed again, waited, observed again, 15 times. So this should have been a very good spectrum with a lot of spectral features. We could have learned a lot about this atmosphere, but we couldn't because it was bad weather. Well, maybe one of the most important things about, maybe not important, but interesting things about exoplanets is the thought that they might host life. We know that there is life on Earth, so we know it's possible for life to exist in the universe, but we only have one data point. We're looking for life elsewhere in the solar system. And we are looking for life elsewhere on other exoplanets. They're a bit further away, but we are trying. So one way of doing this is to look for biosignatures. So when you take your spectra, when you get your spectra either in transmission or in emission, it's probably going to be in transmission, but never mind. Then you can look for signatures, chemical signatures, which you associate with life. So here on Earth, life produces a lot of oxygen. So we could look for oxygen or ozone, which are very good biosignatures. So it's very hard for these chemicals to exist just by themselves. They have to be produced by something. There has to be some process which makes them. Otherwise, they react with everything and they'll be gone. So if we see a biosignature, ozone or oxygen, and if we see them in great quantities, we could infer that there is something going on. And that something might just be life. Another thing to consider is that we would like these planets to be in the habitable zone of their star. And what that means is that the planet temperature, so comparing the stellar light heating up the atmosphere, or the planet, and how much the planet is radiating away in thermal radiation. So doing that calculation, you can find out how hot the planet should be. And you want it to be just right so that water can be liquid, because we know that Earth has a lot of water, which is crucial for life. So if we have liquid water, then maybe the chances of finding life elsewhere on these planets, the probability for that might be higher. So we look for planets in the habitable zone, and in these planets, we want to find biosignatures. This is very hard, but we are trying. So in the future, we are going to have new telescopes with new capabilities. So the spectra that you have seen so far, so this is real data that I have shown you. The data points, although they have been informative to scientists, they don't look like much if you are not trained. However, if we use the James Webb Space Telescope, which just launched not that long ago, on I think it was Christmas Day, which has now been traveling to its Lagrange point, which is where it will stay and do its observations. So this is an infrared telescope. So if you use this telescope and take a spectrum, either in transmission or emission, like I've talked about, then the data will look something more like this. And here you can see a lot of structure. All of these peaks are chemical signatures. So they're essentially the spectral lines showing what types of atoms and molecules you have in the atmosphere of this hypothetical. So this is not real data, because James Webb's Space Telescope has not started taking real data yet. This is a simulation of what we should see from what we currently know. So if you can compare the blue data points here to the red data points, the red data points is what we expect from James Webb. The blue data points is what we got from Hubble, which was informative. We could detect water and other molecules, but now we're going to get a rich spectrum, and we're going to be able to learn a lot. Maybe we'll be able to find biosignatures of planets orbiting in the habitable zone of their host star. So, to conclude, we can do more than just detect planets. And exoplanets are diverse. We have found exoplanets with every type of orbit and with different temperatures, different densities. So the 8 planets we started off with in our solar system, that was just the beginning. And we are trying to now fill the landscapes of what is possible. And it turns out that the universe has greater imagination than anyone could have thought. Yeah, studying the exoplanets. Oh no, sorry for that. Sorry for this technical problem. My iPhone just did something. So, sorry. Studying exoplanets will help us understand their chemistry, composition, and formation. We can learn about winds, etc. So we can learn a lot by studying atmospheres. And what I want you to know is that this is only the beginning. In the next 5-10 years, we will learn a lot more from James Webb. We'll also learn more from other ground-based telescopes, which are coming online within this decade. So stay tuned, and thank you for listening.
Wonderful, Måns. Thank you so much. Really, really fascinating stuff to hear what is on the very edge. The very cutting edge of sort of human knowledge and technology at the same time. It's such a cool area. Questions in the chat. I see some people have found it already. We're going to kick off with this question from CJ, who says that binary star systems are more common than single stars, right? Most stars in the universe are in binary stars. Have we detected any planets orbiting binary stars, and does the binary nature sort of throw off any planet detecting techniques that you spoke about?
Oh yes, we have detected planets around binary stars. That's true. So what tends to happen is there tends to be a hierarchy in these systems. Either you have 2 binary stars that are quite close to each other, and then you might have a planet further away. I'm unsure if we have detected that actually, but the second case we have detected. So we have a host star, planet around it, and then a star which is much further away. And in that case, our techniques that we use to observe these planets are not really obstructed, and things work out fine.
Wonderful. There's a question from Nikki as well. How precise is the identification of spectral data? This is something that we were talking about before the talk. She says that there's a recent controversy about the detection of phosphine on Venus, which is all about the correct interpretation of the data from planetary atmospheres. So how sure can we be when we say that we detect these chemical species in the atmospheres?
That is an excellent question, and something we talk about in our research group every day, basically. So it's hard to know if the detections are real, given that the noise can be quite overwhelming sometimes. But at least everything I told you today is robust. Everything has been confirmed by other observations. So the better capabilities we get, both in terms of interpreting the data that we get and the new telescopes and the observing techniques that we get, the better our conclusions will be. So in the beginning, I agree. It's hard to say anything, but as we learn more and more, things will improve. As for phosphine, there's been a lot of papers discussing if this detection is real or not. I don't know if the jury is out yet. I've read a recent paper saying that although the amount they detected now seems to be slightly less, it might still be robust.
Wonderful. Well, Måns, thank you so much. And thank you to everyone who has been listening at home. This has been an open evening at Cambridge University Astronomy. We do these every week during the winter up until the end of March. And we're going to be back next week at the same time, 7:15 p.m. with a talk all about doing astronomy from Antarctica. So we will see you then. Awesome. Thank you. That was really good.
Cool. Thanks. Yeah, that was fun.
Yeah, nice one. Good work. Yes, I don't know. Are you around the department much these days?
Yeah, I usually go in almost every day.
So are you in your office now?
I am. Yes.
Yeah. Okay. Cool. Okay. Yes, I will. I'm sure I'll see you around the department and say hi. Like, honestly, that was really, really nice. Thank you. Like, you did a good job of covering the basics, but also adding a bit more advanced stuff that you don't always hear.
That's what I wanted, because I knew that like people are into science, they probably know about the radio velocity method,
right? Exactly,
but they don't know like what we have done with atmospheres. We have actually done more than just detecting planets.
Yeah. And even I really like that you spoke about just the problems of measurement uncertainty and fishing around in noise for data, because that's such a big part of what we actually do. And so
that's true.
Communicating that is important. No, that was really nice job. Thank you so much.
Nice, thank you.
Have a lovely evening. I will see you around.
Thank you.